So chapter 23 is all about amines. Amines, we've seen a fair amount in the previous chapters, but I wanted to do some review. Let's go back to the very, very basics. What's this compound called? Ammonia. It's the simplest amine. It's the one that's made through that Haber-Bosch process that I talked a lot about at the beginning of the year. People get this confused all the time with this compound. Ammonium, right? So make sure you're using the correct terminology. Oftentimes amines, if you see them in things like pharmaceutical drugs, they're the ammonium salts of the amine. Does anybody know why you see ammonium salts in drugs?
It's because of our body pH.
Yeah, because they're bases, right? So under a lot of physiological pHs, they'll get protonated anyways. The other thing is that they help impart solubility. So if you've got a nitrogen with a positive charge, it's going to be a lot more soluble in water, right? You want your drugs oftentimes to have enough water solubility to go into things like your bloodstream. We also have a bunch of different types of amines. We've got amines that are primary. Primary amines are where you have one R group coming off, meaning one carbon. You can have secondary amines. You can have tertiary amines. And last but not least, you can have quaternary amines. Quaternary amines are pretty common. They're over-alkylated amines, meaning you've forced that lone pair on a tertiary amine to do some sort of Sn2 chemistry. So this would be primary, secondary, tertiary, and quaternary. Does that make sense? You'll oftentimes hear amines referred to in a different manner too if you're talking about natural products or drugs. Oftentimes you'll hear them called alkaloids. Alkaloids are amines derived from a natural source. So things like quinine. If you've ever had tonic water, that tonic water tastes really bitter, right? That has an alkaloid in it, which gives it that bitter, astringent flavor. If you want a really fun thing to do with tonic water, get a black light out, and it will glow this bright blue color. If you ever go out clubbing, it's kind of fun to see that sometimes. Clubbing, in quotes. You might see me out there clubbing too. I'm just kidding. I hate that stuff. My friend made me go to one of those once, and I was like, why do people pay money to go here? It is loud. So reactivity of amines is really straightforward. You can do really simple reactions like proton transfers, where you can protonate amines, giving an ammonium salt. We've seen that plenty, where they just act as a base. Alternatively, you can react this with some sort of halogen through an Sn2 reaction. And if you do this, really all that's happening is your backside attack, kick off your leaving group, and that's how you can form your quaternary ammonium salts. And it's important to remember that you do have a conjugate anion that's floating around in solution for these, and the property of the salt has a lot to do with the anion that's present as well. You can get different solubilities based on that. That's the really, really basic generic overview of simple reactivity. However, we're going to get into a lot more detailed mechanisms later on. But before we do that, let's review a little bit of nomenclature. Amines are pretty easy in terms of nomenclature. They're the same as alcohols. But with an amine suffix in place of the all. So it's a pretty simple one to remember. Let's try a few simple ones. Actually, yeah, let's do that one. What would this one be called?
Ethanamine.
Yeah, you could call it ethanamine. Oftentimes people don't like the way that flows off the tongue, and so they'll just call that ethylamine too. Either one's fine. Let's try another one. Isopropyl amine. This is really common in organic labs because it's used to make LDA, right? So LDA is lithium diisopropyl amine. It can be made from isopropyl amine. Alternatively, if you're going with the other naming system, you could call this 1-methyl ethyl amine. And if you remember, the numbering system for this is identify your longest carbon chain, and in this case we have a methyl group coming off carbon 1, so you just call it 1-methyl ethyl. Either one's fine. There's also one other one I wanted to show. Whoops. What do you guys think this one's called?
Cyclohexamine.
Yeah, cyclohexylamine. So you will sometimes see it with that YL in there. There's no rhyme or reason to why they choose one or the other. Just choose the one that sounds the best. I won't mark you down if you do it the other way.
So if you said cyclohexamine would be cool.
Yeah, if you did cyclohexamine, I'd be fine with that. However, if you said that to another chemist, they might look at you a little funny. Yeah. Let's try another one that's harder. So this one, we've got two functional groups. Which one's the higher priority?
Actually, no,
Probably
ketone.
In general, carbonyls are the highest priority functional groups, with carboxylic acids being the highest. So in this case, we don't want amine as our suffix, right? And in this case, we want to treat the amine as a substituent. So let's make a note. In cases where a higher priority functional group is present, treat your amine as a amino substituent. Okay, so now we're in better shape.
Shouldn't be amine.
Okay. Thank you. So now if we go through and we number this, we go 1, 2, 3. Why don't we go left to right?
You could have a higher number.
Yeah, you want your substituents to be at the lowest possible number, right? So in this case, we want it to go right to left, not left to right. Okay, so it looks like we've got some sort of propane backbone. And what would the suffix be for a ketone? Yeah, so it'd be 2-propanone, but we need to add in the amino part, right? So what would the overall name be?
It's just the amino propane. Because it's implied it's on the 1. Because it can't be on the 3.
Yeah, exactly. So Brian was saying you don't really need to say 1 because there's no other spot for it to be. So you could just call this amino 2-propanone. However, it's not wrong to say 1-amino 2-propanone. You're just doing more work. All right, let's try a couple others. I'll give you guys a minute to work on these and then check with your neighbor. One, two, three. Okay, so that's one. And this bottom one's a little bit trickier, but see if you can figure it out using the same rules we talked about with naming amides. Who thinks they got the first one? All right, let's quickly go through the first one. Should we number going right to left or left to right?
Left to right.
Left to right. We want the amino to be at the lowest possible position, so I'll go 1, 2, 3, 4, 5, 6, 7. So we've got a heptane backbone. All right. And then stereocenters. Carbon 3, is that an R or an S? An S? I agree. How about 5? R. Okay, so if we go to name this, this would be in parentheses 3S 5R. We'll put that at the beginning. And then dash, and then we want to have our substituents first. So in this case, what should go first? 5-methyl? And now what? Yeah. We want to have 3 for the indication of where the amino group's coming off. So we'd say 3-heptanamine or heptylamine. So this would be the full name for that compound. Oh, thank you.
So why aren't we naming the things coming off of the amino or the amine as two different, like a propyl is on the left and then our 1, 2?
Sorry, say that again?
Well, because in our earlier like basic naming,
Mm-hmm.
the nitrogen was the sort of parent and then other things came off that we knew the things coming off of them. But in this we're naming longest chain.
So you want to identify your longest carbon chain similar to with alcohol naming. And then wherever your alcohol is coming off, like we did before, we said you'd indicate that alcohol position with a number, but now we're just changing it to an amine. So you don't actually include it as a part of your longest chain, but it needs to be bound to that longest carbon chain at one point.
But earlier we were naming things like, let's say there was 2 carbons coming off of the nitrogen. There
Like-
was 2 carbons for the,
Like this one?
yeah, those, or sure, or the one on the left. the amine was like the parent thing, and then there's this.
Oh, I see what you're saying. So for this one, another way of naming this, sorry, let's go back. So you're saying why didn't we number it going this way?
Exactly.
So you could. This one's a little bit ambiguous in that regard. So that's a really fair point. So in this one, you could call this 2-propanamine, or you could call it isopropyl amine.
You mean 2-methylpropanamine, right?
No, in this case, the amino group's coming off of carbon 2, and the longest carbon chain is a propane. So you could call this 2-propanamine.
Oh.
That one is, I didn't even think of that. That one's somewhat ambiguous, but you want to do it similar to like we did with alcohols.
Yeah.
So identify your longest carbon backbone that has the alcohol coming off, but in this case it's an amino group. And then indicate that position with a number.
So when it's maybe bigger and more complicated, it's simpler to name it this way, and when it's just one thing sort of attached to an
Ex-
simple thing, then naming it a different way.
Exactly. When it's a simple one, you can go with this super simple naming, but for the more complicated ones, try to find your longest carbon backbone. All right, next one. What's the parent here? Aniline. So aniline's when you have an NH2 coming off the ring. So now the question is, do we want a number going counterclockwise or clockwise? Counterclockwise, why?
Start with the plural because otherwise you have a 5.
Yeah. So in this case, whoops, it should be 1, 2, 3, 4, 5, 6. So if we go through and we number this, it would be 5-ethyl, 2-fluoroaniline.
Did you call it benzamine?
Sorry, what?
Did you call it benzamine or not?
It would. I don't think really anyone calls it that anymore. Aniline's a very common parent name. All right, and then the last one. Is there a stereocenter in the last one? And if so, is it R or S?
No.
No stereocenter, so you don't have to worry about it. Okay, so longest backbone. Let's go through and number it. We've got 1, 2, 3, 4, 5, 6, 7. So it's a heptane backbone. Now the question is, how the heck do we name this group? Yeah, NN diethyl. Okay, so let's go through and plug that all together. So it'd be NN diethyl 4 heptane amine. So just like with amides, you have to indicate when you've got substituents coming off the nitrogen, but you always want those substituents coming off the nitrogen to be the shortest possible substituents, right? Because you don't want them to be the longest carbon chain. So it can get confusing with some of these, but just practice through the ones in the early part of the chapter 23 in the textbook. All right, let's go on and do a little bit of review from previous chapters.
Do you not put parentheses around the ends?
No, you don't put parentheses around the end. They're capital N's too, not little n's. A little n means something completely different, and I see that a lot. Little n means unbranched, not a substituent coming off of nitrogen. So they have different meanings. All right, so we'll do a little bit of practice here. So if we treat an alkyl halide with sodium cyanide, what do we get? A nitrile, right? It's just Sn2. All right, and then how can we convert that nitrile into an amine? LAH.
Excess, right?
Yep. Followed by a water workup. So you can use this to install amines pretty easily. That's one route we've seen. Let's do another one. This time we have to match the reagents. So what reagents would we need to accomplish this transformation?
Ammonia max.
So for step 1, we can't treat it with ammonia right away. Ammonia will just deprotonate your carboxylic acid. Yeah, let's make it into an acid halide. Followed by NH3 in excess. So that's our nucleophilic acyl substitution, and it also acts as our base, so we need more than one equivalent. All right, then how do we lop off that carbonyl group? LH. It's a little bit weird. And then a water workup as well. So you can make amines those two different ways. The main thing to pay attention to is with cyanide, you're obviously adding in one new carbon, so it really depends whether or not you're trying to add in carbons or not. It's a pretty handy way of adding in one carbon if you use that top way. All right, and then our last review one. Is for aromatic rings. How can we make aniline from benzene?
Nitrate first.
So HNO3, H2SO4. I agree. That's what you guys did in lab, right? You nitrated your aromatic ring. And then how do you reduce that nitro group?
HCl and milk.
Yeah, zinc or iron. It doesn't really matter. And HCl. You can even do this with hydrogenation. So palladium and hydrogen will work as well. Really, any reducing conditions. In fact, when I used to make these in lab, I would accidentally reduce them without meaning to. You have to be very careful with these. I think there was one time, this is completely on an aside, but I was working with a nitrated aromatic compound, and I made the mistake of doing an acidic workup, and I had my metal spatula as I was scraping the sides, and I think it reacted with the metal on the spatula to reduce a bunch of the nitro groups. So it's one of those things where you got to like be very, very careful with these.
I did that in lab with my metal stirrer.
Yeah.
It turned like almost rust colored.
Yep, and when you do that, what you're doing is making aniline, and aniline will quickly polymerize into this big gooey, viscous nonsense. So you have to be very careful with metals when you've got nitrated aromatic compounds.
Second time.
All right, so let's take a look at preparation of substituted amines. Because all of the ones we've seen so far are just primary amines. They're not secondary, tertiary, or anything beyond that. So what reagent would I need in order to make this amine?
Agree.
Yeah, just methyl iodide, right? So Sn2 chemistry is pretty easy. We can do backside attack. In this case, we've got our ammonium salt. And then if you've got any excess ammonia around, this can really quickly reach over and deprotonate your amine to give you your now primary amine. This can work, but it's really, really, really hard to stop at the primary amine. In fact, it'll just keep on going and going and going and going uncontrollably. So despite best intentions, what you'll end up with is your alkylated, fully alkylated ammonium salt. So this is one common mistake I see in organic chemistry is Sn2 isn't useful for primary amines. It will over-alkylate. But if you are trying to make a quaternary ammonium salt, it works pretty well. Quaternary ammonium salts usually aren't desirable products, but if that's what you're going for, you're more than welcome to do Sn2 substitution. So what we need is ways of making primary, secondary, and tertiary amines where we don't run into this problem of over-alkylation. But let's kind of step back and talk about some old school chemistry that you may see on the ACS. So there's one new way we have of making amines using substitution chemistry, and I'll explain why nobody does this anymore. This is through azide chemistry. The overall reaction is really straightforward. You have some sort of alkyl halide. You can make that through radical halogenation. And then you treat this with sodium azide. Sodium azide is a funky looking compound. In fact, let me erase this and spread this arrow out. Where if you draw the Lewis structure for N3, it's got two negative charges on both nitrogens on each side and then a positive nitrogen in the center. And this is a reasonably good nucleophile, so it can attack in, kick off electrons. And then you'd have NaX as your spectator ions. And then in this next step, you've got a couple different routes. One route is just treat this with hydrogen gas and palladium or platinum, one of the two. And you can actually reduce off that nitro or the azide group and get to your amine. The nice benefit to this over the cyanide one is you don't accidentally add in a new carbon, right? We haven't changed our carbon chain at all. The other method involves LAH. I'll show you guys the mechanism for this really quick. So with lithium aluminum hydride, all you're going to do is have a hydride basically attack in, whoop, let me change it to red, to this nitrogen, pick off electrons over here. Let me clean this up a little. There we go. Oops, sorry. I'm skipping steps. Ugh. This arrow is bugging me. There we go. That's alleviating that positive charge.
Okay.
I was like, why don't you get double the negative charge?
Sorry. There we go. So now we've got this intermediate. And then at this step, this negative charge will clamp down, form that triple bond, and then kick off your leaving group. You should have a lone pair on that as well. Why do you think that happens?
Makes nitrogen gas.
Yeah, it makes nitrogen gas, exactly. And then step 2 for this reaction is just treat this with water as a proton source. And you can get to your primary amine. So either reduction condition will work. You can do hydrogen and platinum or palladium, or you can do an LAH reduction. Either one's fine. Oftentimes your choice of reducing conditions depends on whether or not you've got double bonds present, right? If you've got double bonds present, you don't want to use the hydrogenation conditions. However, if you don't have them present, sure, why not? It's pretty easy to do the hydrogenation reaction. Like I mentioned though, this reaction is not popular. Does anybody know why?
That probably looks like it would
Nitrogen
kill you.
gas going on.
Nitrogen gas? Any other reason?
It looks like it would kill you, the
N3?
N3. Looks like it'd kill you.
Looks like it could kill you. Yeah, this is something a lot of people don't appreciate. This is about as toxic as cyanide. I looked it up, and I was curious. The lethal dose of NaN3 for a human being is 0.7 grams, and it gets absorbed through your skin. So if you accidentally spill it on yourself without gloves
You're
on,
dying.
checking out early. So you have to be super duper careful with this chemistry. Most labs won't even let you use these reagents or order them. Oftentimes these azides can be explosive too, so you have to be very, very, very careful anytime you're making azides or working with sodium azide. Do you have a question?
Yeah, I was curious if you chose the route on the right-hand side of the H2 and is nitrogen, is the excess N2 leaving as gas or going to becoming ammonia?
I would have to look up the mechanism for the hydrogenation. Because it goes on a metal interface, I don't think they even include it in our textbook as one that you need to know. So tomorrow when we come in, I'll talk about the more commonly accepted way for making amines known as the Gabriel synthesis, and we'll start doing some more synthesis problems based on that.
Did you look up the